Welcome to lecture 3. We start off this lecture with electric field. What is electric field? Electric field is a force field around a Coulomb charge, okay? But it is defined as the force experienced by a test charge in the presence of a given charge at a given distance. So, electric field E bar, electric field is a vector quantity. It is expressed as limit as q tends to 0, uh, f bar, the force experienced here, divided by charge q. Okay. The SI unit is Newton per Coulomb. So unit is Newton per Coulomb. Obviously, force is measured in newtons and Q is measured in this, or volt per meter. Okay, V by M. Okay, the dimensions of electric field. These are very important from fill in the blanks point of view. L M T minus 1 A T minus 3 A minus 1 T minus 3 A minus 1. Let us see the relationship between electric field intensity and electrostatic force. So let capital Q and small q be charges separated in vacuum. By a distance r. Okay, so Coulomb force F bar is going to be 1 by 4 pi epsilon 0 q by r square into r cap, since we are using the vector notation. Remember that r cap is the unit vector. So electric field E bar can be written as F bar by Q. So this is going to be 1 by Q into 1 by 4 pi epsilon 0 Q by R square R cap. Obviously Q would get cancelled and I'll get E bar E bar would be equal to 1 by 4 pi epsilon 0 uh, Q by R square into R cap. Okay, so this is a very important relationship which we have developed for between charges and electric field. We come to the more important region of this chapter, where we will do our first proofs. There are about 5 or 6 proofs in this, so one of the first proofs we will begin. So we are trying to derive an expression for electric field intensity due to point charge in a material medium. So what is electric field intensity? Intensity due to point charge in a material medium. So consider a point O, and we'll place a charge Q at this point O, and we will take another point B. Obviously distance OP is R. Pardon my drawing here. and we will keep a test charge q0. So due to the electric field produced by this, it's going to generate a, electric field, and that field will be felt by our test charge q0. The Coulomb force F bar would be equal to 1 by 4 pi epsilon 0 k, because it is a material medium. It need not be vacuum. Q0, the two charges, upon r square, the distance between the two charges, and my unit vector. ठीक है. Now, electric field intensity E would be defined as the Coulomb force divided by the test charge Q0. So obviously this is going to be 1 by 4 pi epsilon 0 K. Q0 will get cancelled, so it will be Q by R square dot R cap, which we just did 2 minutes back in the definition. So that is not a problem. So the electric field magnitude of the electric field intensity, therefore, a magnitude uh, of electric field intensity uh, uh, is going to be uh, E is equal to 1 by 4 pi epsilon 0 k q by r square. Okay, observe that since it is magnitude, this arrow is not there. Okay, bar is not there. Now, if charge is in air or vacuum, then my E would become 1 by 4 pi epsilon 0 q by r square, which is a very popular derivation. Now let us define a uniform electric field. A uniform electric field. A uniform electric field is a field whose magnitude and direction are same uh, in all directions at all points. Same magnitude and same direction at all points. Okay, which is a very important thing, at all points. Okay, you can't say sir आधा dozen points पे uniform है तो uniform हो गया. It's not like that. It should be at each and every point. Okay, so uh, say it's like between two parallel plate uh, uh, electric field between two parallel plates. Okay, and non-uniform field whose magnitude and direction is not the same. So non-uniform electric uh, field has unequal magnitude. Yeah, magnitude is not the same. which is not the same at every point. Okay, so that is a very important thing. Now let us find out the derivation between electric field E and electric potential V. A pair of parallel plates is connected as shown in the figure, and which results in a uniform electric field, which is indicated by this arrowhead here. Okay. So the electric field is directed from a plate A to plate B, like this here. Uh, Plate A to plate B. Now, a potential difference V is applied between the two parallel plates and separated by a distance D. Potential V is applied uh, to the parallel plates. Uh, Separated by a distance d. Now, of course, the electric field between them is directed from A to B as shown by the arrow. The electric field is directed from A to B as shown in the figure. Okay, a charge Q is introduced between the plates. Uh, Now, if a charge is moved against the direction of field, so Q is moved towards the positive plate B, plate A. Okay, work would be done. Okay, this work has to be done is because we want to find out the potential. Unless we find the work done, we don't find the potential. Okay, then the work done in this case, W, is going to be force, electrostatic force, into the distance with which through which the work is done. Now, potential difference V between the two plates is W by Q. V is equal to W by Q. This is by definition. Okay, so obviously you can see VQ is equal to FD, or F upon Q is equal to V by D. Okay, but F upon Q is E, is equal to E, electric field intensity. Therefore, we get a very interesting formula. E is equal to potential difference divided by D. Okay, very important formula. So electric field intensity is equal to potential difference divided by the distance between the charge particles.